Section 2.4, Computational Algorithms and their Convergence, will first define errors. Suppose that P star is an approximation to P. P star can be an output of computational algorithm. Then the absolute error is the absolute value of P minus P star. And the relative error is the absolute error divided by the magnitude of the true value. Once P is non-zero, then we can define this relative error, right? In reality, the relative error is more popular than absolute error. For example, P is 1 million, and now assume we have P star such that absolute error is about 1,000. Then the absolute error looks large. However, it's relatively very small. Relative error is 1,000 over 1 million, which is 1,000, so that in percentage it is very small, so that we can accept it, even though the absolute error is large and looks not acceptable, but relative error is small, so we can accept it, and also quite reasonable, right? Computational algorithms. An algorithm is a procedure that describes in an unambiguous manner a finite sequence of steps to be carried out in a specific order. Algorithms consist of many steps for inputs, outputs, and functional operations. Algorithms can be described effectively by a pseudocode. Pseudocode is showing the major operations and easy to understand. And earlier, the algorithms are written in code by using C or Fortran. So it is a very large, long lines of code. So at a glance, it is not easy to understand. So by seeing pseudocode, we can understand it more effectively. But in modern society, if you are using MathTalent or Python, then the code is short enough so that you can understand the whole scope of algorithm and the code quite easily. However, to describe the algorithm more effectively, yet pseudocodes are being used. Okay. An algorithm is called stable if small change in the initial data input produce corresponding small changes in the final results output. So stable algorithm will change small in output from small change in input. Otherwise, it is called unstable. Some algorithms are stable only for certain choices of data or parameters, and in this case, we call them conditionally stable. Growth rates of the error. Suppose that E0 is an error introduced at some stage, maybe initial stage, and En represents the magnitude of the error after n subsequent operations. If En is basically n times of E0, that means that here in each step, around the E0, error will come out, and after n operations, Now, basically, this is n times of the E0, but they may be around there. Each step, the error is around there. However, it can be a little bit large or small, so that we put here a constant C. Once error is coming in this way, then the growth of the error is said to be linear. And in this case, the algorithm is stable. If En is given in this way for some C larger than 1, then in each operation, the error is exponentially increasing. So we say that the growth of error is exponential, and in this case, the algorithm would be unstable. Now we define rate orders of convergence, and Xn is a sequence of real numbers tending to limit X star, and Xn can be an output of an iterative algorithm. The rate of convergence is at least linear if there are a constant C1 less than 1 and an integer capital N such that the error at n plus first step is bounded by C1 times error at nth step. So later error is bounded by an early error times C1, which is less than 1, so that this one is smaller than that earlier error. If error is shrinking in this way, then we say that the convergence rate is linear. So we say simple as linear convergence. And if there is a sequence epsilon n tending to 0, so that later error is bounded by epsilon n and the earlier error, then the error is decreasing faster than this linear convergence. So here, in this case, we say this is superlinear convergence. And if we have here the convergence rate is given in this way, convergence is given in this way, then we say it is quadratic because power 2 is given. And now in this case, C doesn't have to be less than 1, but anyway, a small number. In this case, for example, once we reach the error is 10 to the minus 2, then next error will be order of 10 to the minus 4, and again the next one will be 10 to the minus 8, and again 10 to the minus 16, and 10 to the minus 36, and so on. So quadratic convergence is much faster than linear convergence. In general, we say that the rate of convergence is of alpha at least if there exists a constant C and an integer capital N such that for every n larger than or equal to capital N, this inequality is satisfied. Here, the power alpha is given. Once alpha is 1, then these coefficients must be less than 1. If it is larger than or equal to 1, then this inequality is meaningless. Right? Once it is larger than 1, then even though it is slightly larger than 1, it doesn't matter. Eventually, the error will converge to 0. Okay? So it is rate alpha convergence. Okay. Let's see this example. Consider a sequence defined recursively as here. X1 is to and xn plus 1 is xn over 2 plus 1 over xn. So from x2 and x3, the sequence is defined in this way. And here, the question is find the limit of the sequence. I show that the convergence is quadratic. Okay, to solve such a problem, first of all, you have to check the convergence. And you have to make sure it is convergent. And to check it, you can see behavior of the sequence. So here I added program, and along with that, that is MATLAB code, and x is 2 in the beginning, and x is updated by using the formula here, x over 2 plus 1 over x, and it's updated. So exactly this line is representing that portion, and we try to print out. After 1 iteration, 2 iteration, and after 5 iteration, we have that. So along with such practical computation, you can observe the behavior of the sequence. It looks monotonically decreasing. So it is becoming start from 2 and 1.5 and this number and that number and that number, and up to 10-digit accuracy is not changing. However, it is monotonically decreasing and looks like bounded below. It's not going down below a certain number. Once a sequence is monotonically decreasing and bounded below, then it must be convergent, because it's going down and here, so that from a certain moment it cannot go down. So it should stay at some point. That means it must be convergent. And if we want to prove mathematically, we can prove in this way. Here, first of all, for every n, xn is always larger than square root of 2. And you can check it quite easily. Now, xn plus 1 squared minus 2, then by using this term, you can make this from this one some term squared, so that is larger than 0. And also, you can prove this way. So this inequality shows that that is monotonically decreasing and that is bounded below. So mathematically you can prove that. Of course, to prove this one, you subtract, then along with a little bit of algebraic manipulation, you can reach that term. And this is always positive because xn is now larger than square root of 2. So this term is positive. Xn is now again larger than square root of 2. So the whole thing is positive. That means that here xn is larger than xn plus 1. Okay. Now you can check these portions so that we know that sequence is convergent, so that from this point we can find the limit. Okay, let's say limit is x. Then from here, xn is converging to x, and xn plus 1 is also converging to x, so that once it is convergent, then we can say from this one, x is same as now x over 2 plus 1 over x. Now, after multiplying 2x, we can reach that is 2x squared equal x squared and 2x, so that is now 2, right? And by subtracting x squared, now x squared is 2, so that x is here the positive part, square root of 2. So we can find here the limit is square root of 2. But before writing this line, you have to make sure this sequence is convergent. Okay? Okay, we found the limit, that is square root of 2, and we have to show the convergence is quadratic. And mathematics begins with a definition. What is quadratic convergence? This one. So that is now xn plus 1 minus the limit is bounded by some constant times that squared. So already we found that x star is square root of 2. So let's begin with here x n plus 1 and minus square root of 2. Okay? Then what is xn plus 1? Here that is this one, xn over 2. Okay? That is xn over 2 plus 1 over xn minus square root of 2. Right? Okay. To deal with this one more effectively, okay, let's try to eliminate these bottom portions by putting outside the, so factoring out 2xn, and then we multiply 2xn for each term, and that is xn squared. Now that is plus 2 and minus 2 square root of 2 xn, right? Okay. Now for this portion, and from here we have xx separation, xn separation, in fact. And then from this one we have square root of 2 square root of 2 separation. If we put here minus, then this multiplication will make, each one makes minus square root of 2 xn. So minus 2 square root of 2 xn. That means the right side is the same as 1 over 2xn, and now that is same as xn minus square root of 2 squared. Okay. Now also we know here xn is larger than or equal to square root of 2, so that is now bounded by here 1 over 2 square root of 2, and then we write down here xn minus square root of 2 squared. So that for that one, now xn plus 1, this one is always larger than this value. So its absolute value is bounded by this quantity. So that is exactly the form of this quadratic convergence, right? So we proved the quadratic convergence. Okay? We'll continue in the second part. Thank you.